The second session of this conference of the first day, and this focus, the theme of the second session is focusing around WLCG, the Worldwide Large Hadron Collider Computing Grid. And the reason why this session is part of this conference is of course because NIC, the Nordic E-Infrastructure Collaboration, is coordinating the Nordic Distributed Tier 1 Center, which is one of the 11 nodes in the WLCG collaboration. So this session will consist of 4 talks, and the first speaker is Ian Fisk, which is the computing coordinator at CERN. And he will talk about the evolution of the WLCG collaboration. Yeah.
Thanks. Just a quick clarification. I'm actually the computing coordinator of CMS, one of the experiments. I aspire one day to be the computing coordinator of CERN, but give me a couple of years. So I'll talk a little bit about the plans for the LHC, and I tried to keep this sort of general in terms of what we're doing and what we're thinking about. I can't predict the future any better than you can, so we'll have to look at this in a couple of years to see how I did. So the big deal about the LHC right now is that we're currently in an upgrade. So the machine will turn back on. We turned off a couple of months ago. We'll turn back on in 2015. And the energy when we turn back on will be much closer to the 14 TeV that was the design. We don't know exactly how close it will be. We certainly know it won't be any higher. But whether it's 12 or 13 or 13 and a half is still up for debate. And the luminosity will actually be higher than the design because we've almost hit the luminosity now. And there are about 2 years worth of machine work to do and 2 years of development of detector work. And the machine work is thousands of welds and lots of openings. It's a big endeavor, and so this will take all of the time of the 2 years. The impact on the experiments is quite significant when we turn back on. We expect Atlas and CMS will take data at about 1 kilohertz in 2015. That is about a factor of 100% higher than we had on average during the first run. And there's a lot of reasons for that. The luminosity is higher. That makes a big impact. And then a couple of other things. The percentage of interesting events goes up because the energy is higher. We had one major discovery in the first run. That's quite good, of course. But I think given the cost of the machine, it would be nice to have another major discovery. And we'd like to continue to study this one. There will be a significant increase in the amount of computing, but the significant means about a factor of 2, we hope. If you look at the scale of the computing problem, it is about a factor of 6 higher. And so there's a lot of efficiency gains and a lot of operational improvements that we need to look at to sustain this. So it's a complicated environment, and if you look at the first run, this is the number of pile-up events, so the number of times the protons interact every time the beams cross for 2010, 11, and 12. As you see, it went up by about a factor of 9. In 2015, the plot would be sort of over here. They're talking about 40 interactions per crossing. And the problem with that is this is the time of the reconstruction for the software we had in 2010 in the case of CMS. And as you can see, it's quite nonlinear as the number of pile-up events increase. And at 40, it would be someplace way up here. And so the time it takes to reprocess these goes up nonlinearly. And there was an improvement each year. We optimized the software, we improved it, and basically we got about a factor of 9. And that was good because we had increases that were larger than that. But if you look at then what does 2015 look like, it's complicated, and it also requires a lot of computing. And another factor of 9 is unlikely. These were, you've got the low-hanging fruit, the easy stuff. Every order of magnitude improvement in your software performance requires a lot of work. So looking back at the beginning, so the Monarch model, this is the Monarch diagram from 2000 that said what the computing would look like when we started in 2005. And a couple of things are interesting from this plot. It was developed about a decade ago, and it really foresaw this concept of tiered computing facilities, a tier 0, a tier 1, and tier 2s. And this would meet the needs of the experiments. If you look at these numbers, which are probably hard to read, they're kind of comical. The data rate from CERN out to a tier 1 computing facility would be some number of 622 megabit links. That number we actually turned on was 17 622 megabit links. And if you look at the total disk space that a tier 1 would have, it was about 70 terabytes. Now 70 terabytes of disk fits happily in a single disk server these days. We have about 100 petabytes of storage distributed out. on the various places for the experiments. A tier 2 was no better, sort of 622 megabit, one link to a tier 2, and a tier 2 would have 20 terabytes of disk. Now, this is, of course, has grown quite a bit. And one thing that you can see from this model is it assumes very poor networking. And it assumes a very hierarchical model of functionality where only certain things are performed at tier 0, tier 1, and tier 2. And this is one of the things that we think is evolving in our planning in the LHC. Because when we turned on, instead of having the computing located at one spot, we had it in this very distributed set of facilities, about something more than 100 processing centers on about 4 continents. Now, the one thing you can tell from this is that there are individual sites. It is definitely a collection of sites that then turn into a big computing grid. And one of the things that we're seeing change in our planning is trying to look at it more like a big distributed facility rather than a collection of sites. And I have to say that what follows next in terms of really evolutionary, what I think are very interesting changes to the model, I feel a little bit strange talking to Nordegrid, who a lot of these were concepts that you sort of put into the design of Nordegrid to begin with. So anyone who'd like to say, I told you so, can do it now or later in the presentation. We'll have to see how this thing evolves sort of on the global system. So the evolution sort of looks like this. We started with this real concept of a monarch model, and then a few years later, there was a proposal that it would be sort of a big fog or big cloud, a blob of computing, and the people would sit on the outside and not really know where the jobs were running. The data would magically move around. And we rapidly realized a few years ago that the software wasn't ready for that. And the only advantage to sitting out here on the edge, it was a safe place from the big explosion that was going to happen inside, because nothing was going to work. And so there was an evolution toward a much more deterministic system where, again, you went from tiers of tier 0, tier 1, tier 2. And that's been evolving over the 3 years, but it has a lot of elements of the monarch model left. So one of these things was this concept of the CMS full mesh model, where a tier 2 could communicate with any tier 1. There was at least remote data access, so a data federation was used. And then dynamic data placement. And finally, we're looking into clouds. But it's a very deterministic system. Jobs generally went to the data that was placed there. And that's the thing that's changing. So we're reducing the boundaries between the sites in terms of what their functionality can be. And one of the big changes that you see initially is a change in the mass storage model. So originally, this is very much a high energy physics model where you have a hierarchical mass storage system. You've got an enormous tape archive. CERN's tape archive just crossed 100 petabytes. You have a relatively small disk, typically around 10% in front of it. And you would ask for data, the data would flow back and forth between these things, and it was sort of the ideal system because you had an enormous storage and you could simply ask for anything. In reality, it didn't work. Sadly, it doesn't scale that way. These days, we don't have small disk archives. We have 60, 70% of the space in the tape is also available on disk. And it's so much data that has to go back and forth in such a high volume, and the difference between an access on a tape and a disk is so large that most of the time the experiments are asked to pre-stage, that we're asked to move things manually from tape to disk and then access it there. And so what we're proposing to do is actually separate the functionality of the hierarchical mass storage system so that you'd still have an archive center, a place to store the data for long periods of time, but all of the access would be done in these large disk farms. And it's a very structured move from disk to tape and back. And in fact, what we're looking at is why these two things have to be so logically, physically coupled to each other. Well, if this is an archival facility, the disk center can be located there, can be located very far away. This network pipe can be quite long, though it has to be relatively fast. And so once you've split this, once you've introduced the concept of an archival facility, it's not clear exactly how many of those you need. You need to store the data on archives in enough places so that you are protected against data loss, but you probably don't need 11 tape archives, or whatever we have now. And so the idea would be to introduce a certain number of these large tape archives and put them around places, but then serve potentially even multiple tier 1 facilities from them. And once you've done this, the difference between the functionality of, say, a tier 1 and a tier 2 becomes a little smaller. There's an archival center someplace, but there's a disk and a CPU, and the difference between what a tier 1 center can do and a tier 2 center become a little smaller. And if you look at, primarily it's the idea of support. a tier 1 center is a big facility. It's very professionally run. It's available all the time. A tier 2 center tends to be also professionally run, but usually at a university where there doesn't necessarily have off-hour support. But the difference between them gets a little different, and the model becomes a little bit less monarch-like. So it becomes more of this sort of blob of computing. And that propagates. And so this goes into other elements of the system. So for instance, in CMS, we expect that in 2015, the data rate will be so high that we have to process about half of the data for the very first time using tier 1 centers, not CERN. So the data will come out from CERN, about half of it will be processed at the tier 0, the other half will be sent down to tier 1s to be processed. And that means that the difference between a tier 0 center and a tier 1 center becomes also not so great anymore. There's some low latency activity where you really don't want to wait the period of time it takes you to get it out to the tier 1. But other than that, essentially, a computing center is a computing center. So now we've sort of broken down the barriers of functionality. We're going to go one step further and break down sort of the differences of the functionality between the storage and the processing. So by the time we start up in 2015, all of the computing, all the experiments will have the concept of wide area access to the data. So 3 of them are expected to use XRootD-based data federations. There's also development work on HTTP-based data federations. But the idea of this is it's similar in concept to a content delivery network, that you ask for a data set, and it doesn't necessarily matter where it is, it's served to you. It doesn't matter necessarily that the disk is located nearby, it's served to the processing facility that you ask. And so the way that these work is that you have a user application, it speaks to a redirector, that redirector knows or queries the various systems for where the data is, and it sends it directly back to the user application. These are, Elise has had one of these basically since the beginning of the run. Atlas and CMS are both in prototype phases right now. LHCb uses a slightly different technique, but the functionality is similar. And once you've gone to this, there's some interesting things you can do in terms of treating all of the tier 1s like a big facility. A distributed tier 1 facility, it may sound familiar to you. For instance, the LHC-OPN is 120 gigabits of networking, spread out. It's used at about the 20% level. It's not oversubscribed. And all of the tier 1s are connected to it. And so there's a goal right now is to move the worker nodes that are on these various facilities inside of the domains of the OPN. And what this would allow us to do is basically treat a processing node at a tier 1 as being replaceable with a processing node at another tier 1. And the storage could then be shared across to serve. And this allows this collection of tier 1s, which in the case of CMS is 20,000 processor cores. At Atlas, it's probably about twice that, to work on the same data. And also would allow us to, instead of falling back to the archive at the local facility, we could fall over to XRD if the data was accessible at any other tier 1. This has a big sort of change in the model, because if you have to queue up a tape and stage it in, that takes at least a minute. If a data set is located at any other place over the network, opening that file can take a second. So it becomes, the transparency of the data access increases quite a bit. There's been generally when I give this presentation, there's someone in the audience who says, but we spent a tremendous number of years making sure that the data was on even the same rack or the same node. And there's a lot of skepticism since so much effort was invested. And they ask, well, what changed? And the big thing that changed is the network. If you look, the input size of a CMS raw data file is about 0.5 megabyte. And it takes us of order 10 seconds to process it, which means that we can keep a CPU busy by serving it at an average of 50 kilobytes a second per core. And if you look at the number of cores that you can support with 50 kilobytes a second on a 10 gig link, it's quite large. And even thousands of cores then can be processed using data that's not locally stored. Analysis can be done the same way as long as intelligent I/O is put in. On some things it doesn't work especially well, some things it works very well. The big change here is that you have intelligent I/O and high capacity networks, and the rules have changed. This then extends into other parts in the system. CERN is currently, as we speak essentially, deploying what's called a satellite tier 0 facility in Budapest. And it is about the same size in terms of capacity as the tier 0 center that's located in Geneva, and it is connected by 2 100 gigabit links. The networking between them is sort of 200 total. The round trip ping time is about 35 milliseconds. And to test this for the experiments, they introduced a delay box at CERN, introduced a delay of about 30 milliseconds. and asked if we could tell the difference. And we can't see. We don't see a CPU drop, a CPU efficiency drop with this kind of time. Our I/O is smart enough that things are read a little bit ahead so that they arrive before this time. And we will not be able to tell from an experiment side whether a worker node is located in Geneva or in Budapest, and the storage will be served from both locations. So we begin to see a breakdown of what we define to be the boundaries of a site. So we've taken the functionality boundaries and tried to reduce them. We've tried to introduce better data transparency. And then with these very high capacity networks, we can begin to reduce the concept of what defines two sites as being physically separate. And these 100 gigabit networks are the first ones in production, but they will not be the last. They will be the first of many. And before the start of 2015, we have a variety even of tier 2 sensors that have said that they will have 100 gigabit links in production. So all of these things begin to allow us to think of the data center as a big cluster, and not a cluster of sites. So that's a bit of the change. The other thing is the change in the infrastructure that we use. And I call it resource provisioning, but basically, if you look at this, this is the basic WLCG services, the computing element, the storage element, whether that's Cream or Arc, SRM, various high-level services. And if you look at this and say, what has changed in this diagram in the last decade, sometimes the technology underneath has changed, the labels and the general architecture are almost exactly the same. That's changing. So while it's been stable for a decade, a number of places are looking into what would be considered cloud provisioning. And typically this is done not necessarily for any cloud reason, but it's mostly cluster management. That if you are a site provider, it's much easier for you to introduce a consistent layer across the whole facility and then bring up virtual machines as you need individual worker nodes or specialized services, rather than try to install specialized services on the bare hardware. And so a number of places have asked for this, and everything is virtualized, the services are put on top, and in this model, there's really nothing that would prevent you from putting a CE as a virtualized machine or an SE or anything and setting up exactly the same services you have now, except as virtual machines, but it might not be necessary. And there has been a general effort to sort of short-circuit this, and that looks like this. And this diagram, unfortunately, doesn't really do it justice, but in the model that we have now, there is a resource provisioning system, meaning something that requests that processing be done. It sends pilots down. The pilots communicate with a computing element. They're then put into a batch queue. When they start running on a worker node, they call back and get some work to do. Now, the problem with this is that we run about 1 million jobs a day on the WLCG, and we ask 1 million times of computing elements, would you run this job for me? And all of those pilots run with the same certificate, actually, or a different certificate for each VO, and the answer is always the same. It's always yes. So we ask the same question 1 million times a day, the answer comes back yes. It doesn't really, there's no improvement in the security model for this. And the proposal is that what if we were asking for, I would like 1,000 virtual machines that run my pilot. It's one request, a cloud interface then brings up 1,000 copies of this, and then those pilots come back and get work to do. And this is sort of an interesting simplification of what is otherwise a model that has a lot of authorization, a lot of places where things could potentially go wrong. And this is a new resource provisioning model that's sort of based on the pilot infrastructures and the resource provisioning tools directly. And you, instead of asking necessarily for a single processor core, you might ask for a machine or a group of machines. And you would ask for them for periods of time rather than simply the length of time of a single job. And in terms of trying this out, these are systems that are in production. Both CMS and Atlas are using the higher level trigger farms this way. That we have an OpenStack interface, and the higher level trigger farms are not small resources. They are more than 10,000 cores each. And so it's a big facility. And you put in one of these cloud provisioning systems, you ask for a certain number of cores, you get a certain number of virtual machines back. And in CMS, we've got to about 3,500. Then we exceeded the capacity of the network, and they're currently upgrading the network, because in these models, you actually run at the experiment itself, and you come back and read data over the wide area from the data center. And in terms of sites, we've had, it's not a huge number, but it's a handful, 5 or so sites that have said they'd like to provision their own resources in this way. And so this would be a change. So in the end result, I think you're going to see a change in the way that we do resource provisioning. And you will see some sites that actually buy their resources from a provider and don't want to bring up what looks like a tier 2, where they ask you to communicate directly with the resource provisioning system. There'll be a broader community of people who do the development of things like OpenStack and the cluster management and the resource provisioning. All these things begin to merge. But all these things sort of work together. The work that we've done on breaking down the barriers of the storage system and allowing the data to be transparent and accessed over the wide area is critical, because in these models, the resource provisioning is done, but it's very hard to tell where the resources you asked for actually are. And so without this model of sort of good data transparency and high capacity networks, it doesn't work. And so all of these things kind of work together toward a model where things are more blurred in terms of where they're running and where the functionality actually is. So in terms of outlook, I think in general the outlook for the WLCG is that you'll see a breaking of the boundaries between sites. We're already seeing that. There'll be less separation of functionality and more driven by a concept of support and definition of a facility. And the system will be more capable of being treated like a large single facility rather than a cluster of nodes. And hopefully this will be a flexible and efficient and able to incorporate more kinds of resources into the system, and it will allow us then to solve what is a very large-scale computing problem in 2015 without having it scale necessarily with the number of cores that people buy for us. And that's it if you have any questions.
Any questions for Ian? Then I have a question for Ian. So the WLCG collaboration of infrastructure was developed about a decade ago. If you would have to do it again, redesign WLCG, knowing today's technologies, how would it look like? You would not have 11 tier 1 centers.
I would have 11 tier 1 centers, but I would have 11 facilities that are as well run as the tier 1 centers that we have, that are up all of the time. The concept of facilities you rely on are still very important. I think that if we had it to redo, we would probably not have 11 archival storage facilities. We would have fewer than that. If we had it to redo, we would probably try to adopt infrastructure that was used by a broader community from the beginning. We had a model in high energy physics in general that we would set up an infrastructure and we would be the leaders of that, and there would be large communities that came in behind us. And I think that worked to a certain extent, but what we're finding is that in terms of the kind of facilities that we run, everyone's computing problem is a little bit different, and high energy physics was a little bit specific in some sense. And so that there wasn't this, as I think you've seen by the adoption of other VOs, that it's not, there's more people in the community participating in things like OpenStack than there are in the more strict grid infrastructure that we use in high energy physics. So I think if we wanted to have a better collaboration, if we had to redo it, we would have redone it in a way that was more inclusive, I guess.
So you would not buy the entire service from Amazon?
I would not buy we have looked at buying the entire service on Amazon. It's hard. Our estimate is it's still several factors more expensive than running it yourself. It's sort of the rental car model of things. If you want to have a computing facility for a period of time, it's cheaper to buy it on Amazon. If you want to use it every day, it's better to buy it yourself. Because Amazon does not have their scalability is not so much better than ours that they can charge us less than we can do it for ourselves for facilities that we use every day. We certainly wouldn't give it all to Amazon. But the resource provisioning models that were done in development with Amazon are very interesting to look at.
Okay. Yeah, so let's thank the speaker again. Okay. Have a little present. Okay. And then we move on to the second speaker of this session, which is Michael Kreunacher. Michael was the director of the Nordic Data Grid Facility, which was the organization before Nike was established last year. And Michael will communicate some of his experiences and some of the lessons learned while he was director for a 3-year period, or even more perhaps, 5-year period perhaps.
Yeah, something like that.
So please.
Okay, thank you, Jaco. And thanks, Jaco and Gudmund, for inviting me here. And it was very fun to come up here and see all these happy faces. Of course, I guess it helps that someone shows my picture on the slide next to a pile of money. Then people usually smile at you. So anyway, I'm going to say something about the lesson learned from NDGF. So what I would like to do is to take you a trip down a memory lane, starting from when I started in NDGF, which was the, I think, second incarnation of NDGF. And this is actually what the first slide I did from NDGF, you see here, and that was presented also in Norway, in Bergen, at the No-Tour conference in 2006. So we had some pretty wild ideas back then. We wanted to do a distributed tier 1, and we wanted to do it something that hadn't been done before. And we should do it pretty fast because the CERN accelerator was starting up, well, kind of any second. We all know that didn't really go quite as fast. So we had these things under construction. A lot of things were under construction: computing, storage. Nothing were really planned in that many details. But a year after, we had the organization ready for running the tier 1, and we also had a kind of a facility up and running. We had a lot of different sites connected all over the Nordic countries. A lot of CPUs, the storage was integrated, so we're actually able to present the distributed tier 1 as one entry point for the data coming from CERN. We even had some hardware, and that was the only hardware, which was quite fun because it's very distributed setup. And we also had operations, so we could kind of conclude in the end of 2007 that we were there. We had the tier 1 up and running. We could do. We were interoperable with Alice and Atlas, and were able to take data, and well, everything actually works. As it's always nice to show green plots and green graphs. So the next question was, of course, then we could have closed down NDGF and left it for operations, because that was the first goal we had, and that was kind of succeeded in kind of a year. So moving on from that, we tried to say, okay, what can we really do of different changes? And now we started to enter this period of time for NDGF where the management kind of figured out for themselves what could we look into, what should we do, and where is there a possibility for rationalization, lean things a bit. So what we saw was that we were running two parallel grids in the Nordics. We had the EGGI grid and we had the ARC grid. And we thought, well, perhaps we could streamline that a bit. And then we got hold of Iron Bird at a conference and said, well, we want to jump in and solve this right away. And that caused a bit of frustration all over the Nordic, I think. But again, after a year's time or so, we managed really to merge the operational infrastructures of these two grids and had a shifting between the EGGI funding and the Nordic tier 1 funding, and was pretty well integrated into the European grid at that time, which has been something that weren't really the case before that. Of course, that created some problems, because that meant that we have extra people, because we have suddenly merged two projects, and that gives us some extra people and extra manpower. So we had to invent other things to do, and we were still in this time where we had a board, and we had kind of the idea was to build this tier 1, also to look into other e-sciences, and I'll come back to that in a minute. But I would like to, before jumping to the other e-sciences, as they're usually called, I'd like to talk about this other thing, or third thing, I think that really was a great step forward, something we accomplished. And that was to set up or help setting up the Terina certificate service. And it was based on a student project from Trondheim here, I actually think. And given a bit of help and talking to the right people and pushing it forward, I think it's actually still used today as the way to get personal digital certificates. And it was really a leap forward, because before that it could take 2 to 3 weeks to get a certificate. After that, it took seconds, and it was pretty easy and well integrated, and used a lot of systems that were already in place but not really used that much for anything else. So we had these three kind of goals, and I think these were pretty loud spoken. That was something we need to do: build the distributed Nordic tier 1. and also the merger of the EDGI and Tier 1 operations. We did that one as well. This Pan-European Certificate Authority was perhaps not that well formulated as a goal. It was just something that were done. So why I'm talking about this, I think one of the lessons really learned is that if you set a goal, then actually no matter how difficult it is technical-wise or who you need to talk to or whatever, it's pretty much doable. If you have the right people and you have just reasonable amount of time to do it, then you can do it. It's not really a big deal. The problem is to set these goals and to have them. And infrastructure is really built to support research. It's not and research has goals. They're diffuse, ambitious, unrealistic sometimes, but they have goals themselves. You want to find the Higgs particle, you want to do other things, and that creates a lot of needs to reach to these goals. But e-infrastructure, it's not research, and it doesn't have any goals in itself. And this is why it's very important to have these goals and say, okay, we want to solve some specific problem for some researchers. And it's very important to bear in mind they need to have a problem first, and they need to know about it, and they need to ask you. Because if that doesn't happen, it will be very hard to solve them. So you can't go to them and say, we want to help you. But most often when people do this, they think of you as the old Soviet Union trying to help countries by occupy them. So they probably just say go away or give us your money and go away. These are the two options. So it's very important to have these goals. And if you have them and the proper support to do it, everything is possible, and I think even fast. Okay, jumping to the so-called other e-sciences. Quite often they are labeled this way, which is a bit funny, because other e-sciences usually mean other e-sciences than HEP. So it's, so to speak, everyone knows that HEP is using e-science, and the other ones, well, we would like to have them kind of put into the scheme somehow. NDDF has all the time had this goal. It's actually not new, as Gudmund presented. It has been the part of NDDF all the time to even in the NDDF version 1, to also support other e-sciences. And there's been things going on with bioinformatics, CO2 sequestration, computational chemistry, and other things. The thing were that perhaps they didn't really ask for it. If you look at this slide here, which I've stolen from an old EGE presentation, it's not something unique to the Nordics. It's all over. What you see here is that 5 out of 6 CPUs or usage of the grid or the EGE grid was from high-energy physics. It's put on a logarithmic scale, which kind of I always found a bit amusing because that kind of boosts the other e-sciences, but really they're not really using the infrastructure. It was something that were created for the high-energy physicists. They had a problem, they asked someone to solve it or help solving it. Some of them solved it themselves, and it worked pretty well. But I think in order to have the similar setup for the other e-sciences, we need to have a similar situation. Someone asks for help solving something. I might have said this already. So I think we didn't really have the same feeling of success when we look back on the projects for bioinformatics or for CO2 sequestration. They all fulfilled the criteria set up initially, but I think the lack of this feeling of success afterwards were because the ambitions were too low. We could have done much more easily and have created a lot of other things. But again, no one were really asking, so we couldn't really do it. And I think you should respect that. If there's no one asking, you shouldn't help them. Well, I usually say that e-science is trying to apply for others what you used for HEP. And I'm not really sure that has changed that much ever since. Perhaps it has. Okay. The final thing is the success of e-infrastructure. So how do we measure the success of an e-infrastructure? Again, the goal is really to help or facilitate research, or researchers. You should help the researchers. And you quite often see this one I actually stole from SNCC, that you would like to measure the progress and impact of different efforts and these things. And you see it also from compute centers. They have it in their goals that they would like to see that, really say, okay, we are helping these different groups. But I think that the only way you can actually measure these things is if you do a setup similar, like what you have, for example, for NSF in US when you do funding. Then you put it into the acknowledgement of the papers, and then you can do some counting. So this means that you could say this article was built because of the Nordic Tier 1 and couldn't have been done without it. And likewise for the new e-science area starting up with the coordinators recently hired by Nike, if you had this direct measure, so you could after 5 years, now you have a long period of 10 years, you can really go in and measure and count in articles and papers, see, well, this was done because of this. And if you put it in there, then you have a clear measure. This went to science, this one was in Fys Revé and other things, then you would have a clear measure for the value of an infrastructure. And also you would be able to steer and say, well, perhaps it didn't have any value. Or perhaps you should put it in another way, which was also kind of hinted earlier today. Perhaps the infrastructure should just be something that's embedded into the research project itself, which is kind of what we also see for high energy physics today. Okay, so now reach to the conclusions. The goals of research and infrastructure, insight into the world around us, that's for research. To help the researchers doing so, that's the infrastructure goal and the most eminent goal for infrastructures. And then, which was also mentioned earlier, one of the things that not everyone will stay as a scientist till they are 60 or 70 years old and become professors and that. All this system we have built for e-infrastructures, but also mainly for science and research, is to be a part of the education of excellent employees and researchers for the private sector. And I think that's also worth stressing. So it's important also to have in mind when you're working on an infrastructure or research project, perhaps you should also do something afterwards, because that's also important part, and that is also why it's funded by a society. And by society, I mean really that everyone is paying for this. So you should optimize the use of the fund you got for doing this research and the infrastructures. That's it.
Any questions for Michael? It's a bit hard to see, but no, I have a question for Michael, and that's very much more about your experience as being director for the Nordic initiative. And it also, I think, comes back a bit to the comments made by Kenneth and by Gudmund. Like the organization, you have an organization of the national infrastructures, which can be sort of like a coordination of number of centers. It can be more nationally organized, like in Finland. And then also Kenneth had a remark, do we need a national level? So you do have local levels, you have national levels, you have a Nordic level, you have a European level. So how many levels do we need? And because each of these levels, of course, comes with coordination, and the high levels must be anchored into the level below. So you have lots of anchoring, and in the end, everything is very inflexible, and nothing is moving. So what is your experience with how many levels do you need?
I think the first question you should try to answer is, what do you mean by coordination? It's a really, really fluffy word. So you want to coordinate something. So say you have a coordinator in some kind of science area. I recall Oksana, when she was hired first and presented herself as CERN, hello, I'm the CERN coordinator. At CERN, they couldn't help smiling a bit because, well, are you coordinating CERN now? Or what are you doing? Because coordinating something really means that you have something to say over it. And that's not the case here. You're not really, by being a coordinator in some area where you don't have any kind of governmental power or governance power or anything else, you just have something to say. You can invite for conferences, you can do other things, try to make an environment around it, but you don't really have anything else but showing up and say hi. And I think if you see that there's a need, for example, if you run a computer center, you know there's a director there, and he's coordinating the computer center. And he does so because, well, he can, so to speak, hire a fire or set the goals for the different people and make things happening there. So there's a need for him. On a national level, perhaps not. It's hard to say. If there's a need to shut down computer centers, open new ones, and change the funding between them, then you need some coordination there. And the same on the European scale. But as soon as you have this setup where you have a coordinator without really anything to coordinate, so if he can ask the question for himself, can I change anything tomorrow? And the answer is no, then he might not be needed.
Mm-hmm. So concretely, what was your biggest struggle in your position as Nordic director? Was it towards the European level, or was it you struggle more with the national level, or perhaps even with the local level?
I think the struggle were to as I mentioned before, we had a lot of goals set up initially, and that was very easy to work from. And all of us in the GF were very technical oriented, so we'd like to have a goal and do it and solve it. So I think that the biggest challenge were not perhaps towards any of the specific levels. It was more like, give us something to do. So I think that was the main struggle, to have tasks to solve.
Okay, so you had a solution in search of a problem.
Yeah, I think that's true.
Okay,
yeah.
right. Mm-hmm. Okay. Let's thank the speaker again. Yeah. And then the third speaker of this session is Oksana Spinova, and she will talk about one of the experiments of WLCG, in particular Atlas.
Hello, everybody. I'm the CERN coordinator. That's actually because one certain NTGF director put that on my business card. Anyhow, so I'm actually a liaison between Nordic infrastructure collaboration and CERN, essentially. So trying to synchronize things. And I'm also a proud member of Atlas collaboration, and that's what I'm going to talk today about the status of Atlas computing and future plans. Some of those plans you already have heard from Ian, but I will really try to put numbers and some little bit more specifics, especially in the Atlas context. And so this context is particularly important because Atlas is actually the lead user of existing NDGF Tier 1 and also Tier 2 facilities which are coordinated by NAIC. And you see this graph which was taken from the accounting system just a few days ago. So this green color is number of Atlas jobs being executed at the resources which are somehow located in Nordic countries and coordinated by NAIC. And you can see hopefully the count, so it's like measured in like many thousand jobs. And this is May. Actually, LHC is not even running. We are already in a shutdown, right? That's right. And still we have actually very heavy load, and you can only imagine how much this load will increase once the LHC will be upgraded, will come with more data. So this is our challenge, the analyze LHC data. So this is true for Atlas experiment as well as for the CMS experiment Ian was talking earlier. So these numbers are actually the original design figures for the accelerator. We didn't reach the Plan B manager yet, and that's what we are aiming to come closer to after the upgrade. But as you already heard, we already obtained much higher luminosity, which actually means we do collect not only a lot of data, but also these data are rather complex. And then when we look to discoveries of like Higgs or maybe some supersymmetric particles in future, then we will have to do really do careful sifting through the data, because the event selection rate could be 1 in many billions of those events. It's worse than looking for a needle in a haystack. So it is. So while our algorithms are perhaps not as complicated, and they do not necessarily require parallel computations and stuff like that, they are fairly simple selection criteria which our instinct signal should satisfy. But we have to sift through such a huge amount of data that it really becomes a challenge. So, what is this Atlas experiment which collects this data, at least in my case? I show this slide usually only in the Nordic, well, if you can read it, it's actually produced by Swedish companies, so everything is in Swedish here. It kind of illustrates the complexity of the Atlas detector. It's not actually one detector, it's like a huge factory with many subsystems which do detect different kinds of signal which produce different kind of information, and all of this has to be combined, has to be processed, and by magic appear at the personal workstation of the scientist. Well, one piece of magic is missing right here in this big picture. There is no really much of computing infrastructure except of this funny rack of old PCs. It's actually much worse than that nowadays, as you have heard from the previous speaker. We do use worldwide grid in Atlas, like everywhere in WLOG, and so this picture shows the so-called multi-grid infrastructure of Atlas. The picture is a bit outdated, but the point is pretty much the same as was shown earlier. So there is a tier 0 facility, which is CERN, which collects all the raw data and stores and archives everything on tape. While actual processing and most of user analysis actually happens elsewhere. And in Atlas case, there are 3 distinct, for different reasons, infrastructures. One is in the United States, the Open Science Grid, the leftmost part of it, which has one tier 1 and several tier 2 centers around. Then there is, like historically called here, the EGI infrastructure, although actually NDGF is also part of EGI, but there are some differences from the operational point of view, from the middleware point of view, so it's, and from hierarchical point of view. So while EGI still kind of maintains this more or less hierarchical structure, and NDGF is more like a mesh. But anyhow, Atlas tries to make use of all those resources. We're not really picky because we need to use as much as we can lay our hands on, really, and as efficiently as possible. So this slide illustrates the workflow of an Atlas task on the grid. So all the initial data are being stored at CERN, and then the distributed data management system of Atlas triggers data transfers from tier 0 to tier 1s, then further to tier 2s, and perhaps back when it comes to simulation, because it's not only data analysis which we do, we actually do a lot of simulation of physics process to compare with our real data, because simulation is actually essentially our model. And how do we know that we have a new unexpected signal? We actually compare with a model, and we see if this is consistent or not consistent with the model, so that, and see whether we found something new. So we actually need quite a lot of simulated, modeled data there. Further on, actually, this tier 2 is not really the last element in the chain, as you already heard. There are actually a lot of analysis going on tier 3s or even off-grid sites by individual users. But this is not handled by the central system. These transfers are more or less triggered by users themselves. And there is a production system which makes use of the, which kind of triggers data management system to move the data, collects descriptions of tasks either from the centralized system or from individual users, and schedules the jobs normally where the data is. And even if data is not there, the production system would trigger the data management system to kind of pre-stage data there to optimize the processing as much as possible. And data are all different. So this graph here shows all different kinds of data. So in the end, the users are working, the scientists are working with the so-called n-tuples, which are essentially lists of specific observables, which are derived from raw data in many complex steps. And this process of deriving final data from the raw data is in itself actually pretty much resource consuming procedure. It's not in one procedure, it's actually an entire rather complex workflow of splitting and merging and splitting and merging again. So how did we perform in 2012? So these are slides provided by the Atlas Computing Coordinator. So these are very official numbers. I will come to a more close description of CPU and storage usage by Atlas. What is interesting here in this slide is how we can compare what predicted usage was and what was the actual usage of resources. And you can see that, for example, at Tier 1, we used quite a deal more of resources than we expected in 2012. One of the reasons is, of course, that LHC run was extended, and the other is that we actually, well, we discovered a new particle. We had to run many more analysis jobs and many more simulation jobs to make sure that this is really the thing what we think it is. And it's even this difference between the prediction and actual usage is even higher for tier 2 centers, where actually most simulation and analysis is happening. So you see, we can predict, we can try to predict the future, but you can see that we can be actually off by a factor of 2, perhaps, especially when it comes to CPU. It's not that the differences also exists in the data part, but not that much. And we're actually very thankful as physicists to all those computing centers, to all those experts which actually did provide all this extra computing power and this a bit of extra storage, because we actually need it, really. Even though it was not really promised or anything, but it was available for us, and that's why actually we've been so much successful over the last years. Of course, there is a challenge for us to optimize the CPU consumption. Of course, we should do better with our resources. So we cannot really rely that we will get more than we need. So here is more detailed look at the CPU usage at tier 1. You see, so this red line saying pledge is actually what we were promised by tier 1 centers to get in terms of computing power, and you see that we used actually quite a bit more. And for tier 2s, you see this difference is also even more impressive. Different colors here indicate different kind of processing. So this dominant blue color here is actually simulation. So simulation, and this purple is user analysis. So you see that physics analysis actually doesn't take that much resources when compared to actual simulation, which probably indicates some direction where we can improve on our efficiency of resource usage if we want to stay within the original envelope of available facilities. So I just added this slide to show how much is Nordic contribution. So here different colors correspond to different countries, or to different rather regions, not really countries. Although in many cases, like in the case of United States, which is the biggest provider, or United Kingdom, that we one country, but this light blue color is actually the Nordic share. So it's not too big, but I wouldn't say it's negligible. So actually it's quite a substantial contribution, which we should all be proud of. And this is disk usage. It's only for Atlas and only for tier 1, tier 2 in 2012, and you see that it consistently grows. Different colors here show different kind of data. So this expanding band shows the data collected in 2012. So naturally, we get more and more data towards the end of the data taking, and this gray line is actually corresponding simulation. Those shrinking lines are older data. It's not that we get less data, we just get less copies. We try to get rid of those unnecessary copies to free storage to accommodate for a new data. But like I say, the accelerator was stopped actually in February, but that didn't stop data growth. So this slide shows essentially the same thing, but split per those regional clouds. And actually, this is all. This is not only tier 1 and tier 2, but also tier 0. So this top band is actually CERN. And I tried to indicate here the moment when the accelerator shutdown started. And you still see that there is probably not as prominent, but still an increase of total data being accumulated for Atlas alone. So this challenge never disappears. It's always there. We never have a breakdown in this kind of activities. So just for completeness, here is a slide about tape usage, and here we were actually, so this is the tape storage being used at tier 1 facilities, and you see we're using slightly less tape than we expected, although actually, well, mostly because we moved all of it to tier 0, so we mostly archive our data at CERN. So what shall I say about our computing resource usage expectations in 2 years to come, or rather 3 maybe years also. So far we've been utilizing our resources in full. This year we're kind of taking a break, so there might be more partial reprocessing of the older data. We may run more multicolor simulation and just to support more analysis. And of course, there will never be a lull in user analysis. Of course, physicists will be sifting through the data over and over again. Next year, we are really expecting to simulate more multicolor samples for the high-energy run, which is coming, and also like generic simulation, but also on request of specific physics groups. We will do final reprocessing of the older data. The reprocessing is always needed because many things change. Your software changes, your calibration parameters change, and so forth. So this is a regular procedure there. And we actually have to run like full dress rehearsals for the actual startup of the run too in 2015. And then in 2015, of course, we'll start getting new data, and yeah, everything will start all over again, but with the on a higher level. So when we try to project our resource consumption for year 2015, when the accelerator starts again, we have to make quite a big deal of assumptions. And when we do really most modest assumptions, when we think that, for example, we won't require too much simulation, although we would like to have as much as possible. If we set event sizes to be equal to what we had in 2012 and so forth, which is probably none of this is actually true, but trying to do at least some sense of those, trying to come with some numbers, we can do some prediction overall for this tier 1 and tier 2 CPU and storage requirements in the year 2015, so which is shown here as a graph. The interesting part that those horizontal marks indicate, and that's for tier 1 and tier 2 integrated summarily. So this green line shows actually our current usage of tier 1, which is actually quite close to what we expect to have in 2015. And for tier 2, it's much higher already now. So we know that our predictions will be wrong, actually. So we know that we will need to get somehow hold of more resources, or we will have to do something with our code. So what are the opportunities here? So we have to really use everything what we have, and also we'll have to accommodate for peaks. For example, if you look at the distribution of CPU time usage, you'll see that although it is sustained high load, there are some peaks there, and that normally corresponds to conferences because people suddenly have to produce more data on a very short deadline. They always come unexpectedly. So we can try to optimize somehow to streamline our workflow to make better usage of all the resources which we have. But we also are looking now to places which we didn't quite do before. So we are seriously considering usage of high-performance computing resources, really like those in praise. We cannot probably use it for all possible kinds of workflows or tasks which we have in Atlas, but for example, for simulation that's fairly feasible, and we can probably do that. And we do look in the cloud resources, including even probably commercial clouds, especially when we talk about necessity to accommodate spikes in our processing, which we cannot do on a short notice with existing resources. And then buying a bit from Amazon is not a fantasy. Actually, there was this the experience in the United States. Actually, like 5,000 job slots was added for the Amazon from the Amazon Elastic Cloud for actual physics analysis from LHC. So to make it not an exception but a rule requires, of course, a lot of work. So here comes this question of manpower. So what do we really need is actually human expertise, really the human brain to optimize our code and to learn how to make optimal use of as much resources as possible, including HPC facilities and clouds. So there's quite a bit of things to do. So and there are two aspects here. One aspect is when we talk about improving our workflows. So one part is actually Atlas-specific software, which only works for Atlas. Another part is actually distributed computing software, which is something different, and which is not only Atlas-specific. So, and there are ways to improve in both areas. So in Atlas, we definitely have to look how to improve our simulation. As you have seen, this is really the major consumer of all the resources, all the simulation procedures. We have to admit that we are not too good with using, we're not actually running parallel jobs. We're not very good with vectorization. We are not too good with using GPUs and stuff like that, because we were doing pretty much straightforward calculations, which is not too efficient, as we all know. So we have to invest into optimization in these directions as well. We have to look how can we decrease actually event size. Removing some data from the event record is not too good because, well, it's a pity, we'll lose data, right? We can reduce number of copies, but that reduces our redundancy. What happens if disks do crash, right? So what do you do if the copy disappears? So it's a tricky thing. It's difficult to solve, but some solutions will need to be found eventually. And one of the big things, as I guess many of you know, of big issues with the Atlas processing is actually quite high memory footprint, and that becomes a limitation in several places. So we cannot actually, there are some resources, some computing facilities which we cannot use because of the excessive memory footprint, and something we have to do on the level of our software, experiments with specific software, how to deal with that. Probably involving also parallelization, concurrency, things like that. So that will imply actually, if we change our internal computing model, that will imply changes in distributed computing. And there are several activities going on in this area as well. So for example, we are coming right now with a new distributed data management system, which I'm not going into details, but it's actually using quite different architecture comparing to the old one, and hopefully will improve our throughput. We of course are really investigating all the opportunities which are open with improving wide area network data access, which Ian was already mentioning. So I won't mention more about that. We're looking for the new production system for Monte Carlo. And there will be really a new design released actually very soon, like right now. So we're looking how to optimize our network. For example, looking in different ways how to make it different for different, how to make optimal use depending on your application. And like already mentioned, we have to somehow include HPC resources, clouds, and whatever can compute our data into our distributed system. So it's a big laundry list. We have to be well in time and to the coming LHC run 2. And actually, we have to keep in mind that this is not the end of the story. Right now, we were in this stage of run 1, where we collected actually quite a lot of data, but on this wonderful graph you almost don't see this pink line there indicating amount of data collected at this parameters of the accelerator. In 2015, with this run 2, we will collect quite a bit more of data. But then, there will be in the year 2019, as we plan now, the ultimate upgrade to the ultimate luminosity, as much as we can actually reach with this machine, which is above even the design. So there will be quite a bit more data. And if our ideas about this high luminosity LHC, many years from now, will become true, then we will collect actually 2 orders of magnitude more data than we are dealing right now with. So something to think about. And the interesting part that we have pretty good ideas how to upgrade our machine to these new parameters. So these technologies are pretty well known, we just have to deal with them. What we don't quite know is what do we do computing-wise to reach this scale. Not yet, anyhow. So, as for Atlas, I can only repeat that there are many things to do. We have to find how to improve our code. We have to find commonalities. We have to find essentially we have to find the ways how to spend our how to efficiently use our resources, including manpower, which is the most precious resource here. So we have to collaborate with everybody, with other experiments, with other sciences, with resource providers, with everybody to reach our goals. And since we've been asked to conclude with some key messages, there are probably different key messages for different people in this room, but what I thought might be most significant in terms of e-infrastructure is that actually with this advanced scientific instrument like the LHC collider, we can only create this instrument with the help of large international community. So in a sense, our laboratory, it's not like with chemistry case when your lab is in your university, it's not like that. My lab is actually in Switzerland, and I'm sitting myself in Sweden. And even that is not true, because that lab cannot accommodate the data it collects. CERN alone cannot store and process all the data which are being collected by the machine. So actually the computing infrastructure is not in the lab anymore. It is getting distributed all over the world. So in a sense, this worldwide computing infrastructure, it becomes a part of CERN experiment. So it's not a laboratory in Geneva. It is actually a worldwide scientific laboratory thanks to the e-infrastructure, which we managed to build also with the help of Nordic experts. Thank you.
Any questions for Oksana? No questions for Oksana?
No, there's...
Oh, there is one. Yes, please. Yeah.
I found it quite interesting that you mentioned that Atlas is using both for computing and data storage above pitches. Could you elaborate on whether this was because the centers managed to find additional money and purchase additional resources, or whether this is actually because you managed to use unused resources from other projects? So is this actually an example of the sharing that you could benefit from across VO-wise, or is it just because extra resources were involved?
It's a bit of both, but I would say most is really because of this grid infrastructure, which is fairly flexible. It's really possible, especially with CPUs. I mean, you cannot reuse storage, right? Once it's taken, it's taken. But with CPUs, and when you have sufficient flexibility in your system, you could really borrow unused CPUs from other virtual organizations, from wherever they are. So that's probably the major contributing factor. Although there was also the part that, yes, there was some increased funding as well in some cases. So it's a bit of everything. We're trying to get hold of all resource.
Yeah, no other questions? I have perhaps a simple question for you to answer now. Like the accelerator was switched on a few years ago. It is now switched off for a while, and then it will be upgraded, and then after the upgrade it will take science now to the next level. But from all the experiments, of course, there are tens of petabytes per year, and perhaps after the upgrade it will perhaps be hundreds of petabytes that need to be of the raw data that need to be stored. Would there be a scheme where actually there at some point the amount of data becomes so excessive that you say, okay, we're going to throw away the data and we will just regenerate it whenever we want to do a specific experiment?
Well, no, I mean, we won't throw it away. We'll archive them. We'll put them on tape on somewhere and wait for better technology to come and to look at them. So I don't think we will ever throw away anything.
No, but it's sort of like an option, just in case at some point the amount of data becomes so excessive that it becomes impossible to handle.
It is. Yeah. We're actually getting there already now. I mean, for example, in CMS there was this, or there is this approach of parking data for later reprocessing, because simply, we have so much data that we cannot really promptly process all of it for all possible purposes. For some priority purposes, we can do it, but we cannot possibly extract all possible physics analysis because we simply, have those resources already now. So it's not a remote future. It's not a fantasy. It's actually the case now.
Okay.
So we store the data, we archive them. We hope the tapes will hold for a while, and we'll come back later to look at it whenever we can.
Okay, let's thank the speaker again. Some chocolates here. Yeah. And then we move on to the last speaker of this session, which is Stephen Newhouse. Stephen is director of EGI.eu, which is the central seat for the EGI collaboration, the European grid infrastructure. And it was established a few years ago, and to some extent a spin-off very much of activity which started at CERN almost a decade ago. And EGI has a more general purpose objectives, and also not only serving high energy physics, but their primary customer is very much high energy physics. And Stephen will just talk more about these issues. Steve.
All right, thank you very much. So I was originally invited to talk very much, I felt, about WLCG, and as we've already heard so much about WLCG, I was going to try and broaden out a bit more about our support, our planned support for the future, and not only what does that mean for WLCG, but what that means for the other communities that we support as well. So, those of you who are speaking here will have realized that you had a large number of instructions from the program committee as to what to talk about and how to structure it, which was very welcome. So really my big thought for the day is really to pick up on the past activities. And those who don't learn from the history are doomed in a way to condemned to repeat it. And this also picks up very much on the conference theme of thinking very much about how we can learn from the past as to what we do in the future. And I think this is very important because we're reaching the end of the big burst that we've done over the last 10, 15 years in establishing e-infrastructure as a first-class citizen within the research environment. And what we're now facing is how do we sustain that activity that we've already built and the user communities that are built around that. But then how do we go beyond that and start building a new set of research communities and expanding the sort of infrastructure that we put in place. And the strong collaborations that you have here in the Nordic region are obviously one way of building that consensus about what the new functionality should offer. So obviously, where have we come from? So we've come in the last 20 or so years from the World Wide Web that came from CERN to the grid, which built on top of the internet and the protocols that have been established. And from that, in 2010, EGI and EGI.EU was established as a way of sustaining that activity into the future. Because it had already been realized through the work with WLCG and other communities that when e-infrastructure becomes successful, people start depending on it. And as soon as you start depending on something, you need to have a way of it continuing beyond the project cycle, and a way for people to be responsible for the delivery of that service. And we can see how important that is at a basic level through Wi-Fi, email, and things like that. We had the discovery last year of something Higgs-like, which demonstrated how a collaborative environment for e-infrastructure can yield critical and vital scientific results. And so the question then is what happens next and what can we learn from what we've done in the past when we start planning towards our future. So EGI has spent a lot of time over the last year, 18 months thinking about its future. And we've established 3 critical areas that we wish to focus on. These are the community and the coordination and engagement of that community. And Gudmund this morning already established how important the humans within the network are to actually building an e-infrastructure and building a community around that e-infrastructure. What we do within EGI and what we do within e-infrastructures in general is offer a service. Whether that's a service at a single center, such as an HPC service, or it's something that EGI works on, where we federate and bring together an operational infrastructure that runs 24 hours a day, 7 days a week. That requires a coordination function and a commitment to delivering a service. And so that service element of EGI is again embedded in our DNA that we want to do for the future. And then finally, the virtual research environment. VREs traditionally have always focused upon the web portal, but in reality, a researcher needs to have not only a means of accessing e-infrastructure such as the web portal, but also a fair degree of customization all the way from the portal level down to the base of the infrastructure itself. And we've certainly seen over the last decade what one research community, WLCG, can do when it has control over the whole stack. We've also seen how restricted other research communities can be when they do not have control over the whole stack and have to pick up on the infrastructure that's provided for them. And I think one of my lessons to be learnt from the last 10 years is that to engage in other research communities in using your infrastructure, they need to be able to adjust it and personalize it for the way that they want to use the infrastructure, and not to have a service given to them that they have to use in a take it or leave it environment. And there's more details of our strategies available on our various websites. So just to establish that EGI is European-wide, I was surprised to see that NDGF was sort of semi-separated off logistically, perhaps from EGI and Oksana's slides. We see the Nordics as an integral part of EGI's activities, and they've been very supportive in the work that's been going on over the last 4 years and instrumental in helping to set it up. EGI is about delivering federated access to resources and secure federated access to resources. The actual resources themselves will change over time. For the last decade, our focus has been very much on the compute cluster, but with the advent of clouds, we're seeing a growth of interest, and we actually now have a very active federated clouds activity that is looking at bringing together those individual site cloud resources and ensuring there's a consistent way of accessing those resources and of using them and reporting and monitoring them the same way as we've been doing for the last decade about clouds. So the communities that we support are varied. I don't have time to go into them all, but what's common across all of them is the challenge of extracting knowledge from the data deluge that they have coming down from either their computing calculations, from the instruments that they have, from sensors, from the whole load of different data sources. And this provides a unique challenge, because what we have to do is provide those scientists with a digital infrastructure that enables them to do this knowledge discovery. And that provides many challenges for us as infrastructure providers, but also many challenges to the research communities themselves. Many of these communities are going through a paradigm shift from more, say, paper-based ways of doing science to more electronic ways of doing science. And not only do they have to shift their own technology, but also recognizing to deal with their data volumes, they need to move into a more collaborative way of doing that science as well, either because their resources are distributed or their collaborations are now very much distributed because everything's operating at a larger scale. So one example of that is obviously the WLCG partnership. It is a federation of federations. It was good for Oksana to recognize that, which shows that in EGI there's a focus, in Europe there's a focus on EGI in coordinating resources on behalf of WLCG. In North America there's Open Science Grid, and obviously there are other tier ones that are now being established in Korea, Russia and elsewhere. The services that we provide to WLCG are really driven by two important aspects. One is the operation of those services. We have a whole operational infrastructure that we develop that enables the sites to communicate with each other for problems to be resolved, accounting and monitoring, and so forth. And this, in a sense, is our secret sauce that is something that has come out of the community over the last 10 years. The second thing we have are the services, the capabilities that we offer from the services that are deployed at the individual resource centers and by the research communities themselves. Clearly, the experiments within WLCG have their own sets of services that they manage, but they very much build upon the services provided by the individual sites. And so that delivery of that site infrastructure is one of the main things that we do on behalf of WLCG and on other research communities and virtual organizations that make use of that. And finally, we have the sustainability issue. Sustainability is a wonderful discussion point. We don't have enough time in this conference to pick up on it. but it's a key challenge of how do you balance a project life cycle measured in 2 or 3 or maybe 4 years with a research plan, as you saw in one of Oksana's closing slides, that is planned out to the 2020s, 2030s and beyond. And that's something that we do need to really consider as e-infrastructure becomes established. So all this leads to the challenge of how do you do change but do it sustainably? And this really boils down to what are the services you're producing and who plans to use them. The services are varied that people need, but also the services they use are exposed to them at different levels. Ian Fisk's presentation made no mention of EGI, and in many ways, why should it? As a scientist, as a researcher, his focus is on using the services that are exposed to him as part of his research environment. And those within the HEP community come very strongly from the individual experiments. Behind that experimental infrastructure are the services coming from OSG, EGI, and other service providers that enable that experimental infrastructure to be operated effectively. So we have both a direct and an indirect exposure of services to those that consume it. And so while we look not only to sustain the services that we have, we also recognize that services is going to change, and that service portfolio will vary over time. Again, we've already heard in this session how the computing models were envisaged with Monarch 10, 15 years ago are also changing now, not only changed over the last decade, but will continue to change as the new networks, new technologies, and new resource types enable different computing models to be built. So the set of services that need to be sustained at any one time will change. And so we need to be flexible enough to handle that as well. We also need to think about who are the ways that these services can be provided. We have a tradition in the research community of resources being funded centrally, and the researcher has no knowledge and no care as to how those resources come into being, and they are allocated those resources from peer review. This is a well-established model within the research community. It is not perhaps quite as well understood and recognized elsewhere within the policy space, and certainly perhaps not at the European level. Their models are much more around perhaps more responsive, more immediate. So, the UK over the last decade has gone through a model of looking at all of its research activities being funded through something called full economic costing. So research in the UK used to be funded partly through grants and partly through a sort of an infrastructure pot. And that's now moved much more completely to a grant basis. The European Commission talks about many things. One of the things it's talked about is trying to put researchers more in the driving seat in terms of controlling the way research infrastructure and e-infrastructure is provisioned for them. There seems to be a feeling, falsely, that somehow service is not being delivered to their needs by giving them funds to go off and purchase services from the e-infrastructure providers or other service providers, both in the public or in the private sector. We'll have to see how this policy initiative develops and what support it has amongst the member states. But not only will the services change that we need to use and deliver to our researchers, but the funding cycles behind them and the funding models behind them will also evolve, and that is something we also need to be prepared for. And I've already touched on this, the issue around the service dependencies. The services that I deliver may not be immediately visible to a researcher in their lab, but I switch those services off, and the services that compute center depends on to deliver the services to that research community may stop working. So how do we express that dependency when it comes to acknowledging the work and the resources that researcher depends upon for delivering their science and delivering their new innovation. That's something, again, as a community of the infrastructure providers, we have to start tackling. So at the moment, EGI is supported through the EGI Inspired project, which has enabled us to investigate and develop the infrastructure that came out of EG, and to start focusing upon what are the elements that we wish to sustain beyond the end of the EGI Inspire project, and which are the elements that we need to get external funding coming into the community to carry on the development of the service portfolio. Some of those funds will come from the participants within EGI.eu, and some of those funds will have to come, if we can get them, from the European Commission and other project funding sources to develop new innovation and activities. So if you look at our service portfolio, in the broad sense of the service portfolio, it's everything from the things that the staff at EGI.eu in Amsterdam do in terms of coordination, all the way down to the activities of the individual resource centres, the 350 resource centres that are federated into EGI's activities. And then alongside that, there's the supporting activities that we depend on from the middleware and the policy activities that go on. So one of the things that's come down at the lower level ultimately is the open compute and storage infrastructure that provides the resources that the researchers access. We're seeing a shift from very much the middleware as being the way of accessing those. The individual services coming out of the EMI and the IGE projects, which have now come to an end, to seeing how, as those projects look to sustain their outputs, delivering those components from individual product teams. So moving from a much less coordinated view of software to a much more community-driven and demand-driven view as to the software that's needed. We also see a lot of a shift towards the virtualization, and this has already been touched upon again in this session. Virtualization technologies, both commercially and publicly available for open source initiatives, and also through commercial and public sector providers, offer a new way of delivering a software environment to research communities. What's great about them is it's a much larger community that's working on those activities, and that enables better sustainability for those core software technologies than just relying on a niche community such as Grid in terms of working on them. But also at the top level, there's a large amount of coordination that EGI does through EGI.eu and also through partners within the community that delivers those services. Again, I don't have time to delve into that full service portfolio, but it's a rich service portfolio, some of which focuses very much on the coordination of the infrastructure, and other services focus on how to grow and expand the infrastructure around it. And those different services will each need different ways of sustaining their activity. Implicitly or explicitly, those services, at some level, are needed by WLCG. And one of the challenges that we have, perhaps I have, is explaining to the WLCG community exactly how their support and their engagement in delivering these services is important for them to get them back and consume them within their own research activities. So looking at sustainability, we see many different ways. Resource centres have very much been in the public sector funding regime, but with the advent of cloud and as resource centres move towards cloud, the question will be asked, as was asked earlier, why are you not using commercial resources to provide that capacity? And the answer that we've already heard, which is an excellent one and quite correct, is that for things that you use every day, the public sector is still providing good value for money, but the commercial sector does have a role in perhaps providing that burst capacity around the conference season, and also as a way of providing unique resources. If you want a virtual machine that's got a large amount of virtual memory there, it might be that you have to go to a commercial provider to source that particular resource. Service coordination at a national level has many different shapes and forms. We've already seen in Gudmund's diagram the different sizes of the Nordic coordination activities. That diversity gets multiplied when you go out across the whole of Europe. Also, the funding mechanisms behind that also vary. Some centres, some national coordination centres are funded as a part of the annual e-infrastructure budget of that country. Others are still on a project basis, having to apply every 2 or 3 years. And some countries have gone for a subscription basis, where the individual resource centres pay into a pot that supports that national coordination. Some countries go for combinations of all three. But that diversity is something that makes it very hard for one model, again, to fit all of the activities that we have. And then at the European level, the challenges are very much between the generic and the domain specific. It's very easy or it's easier to justify funding a generic service that's going to be used equally by all research communities than funding investment in a set of services that are only going to be supporting one particular community. So we've seen, and has already been pointed out, that the services that we've been funding for the last 10 years that should have been supporting a whole range of research communities have failed to get hold of the traction for that to happen. And so it becomes very hard to look at funding, continuing to fund those services, if nobody outside of high energy physics are using them. So the sustainability of those services is likely to shift much more towards the communities that are consuming them, rather than it being expected to be provided as part of the generic infrastructure. So within that European coordination then, we've been looking at our service portfolio and trying to understand what are the critical services around that. Now, are there services that, bluntly, if we do not fund anymore, nobody will notice? Or we can rely on another partner to deliver that functionality for us? So are there services that if we turn them off today, everything is going to go to pieces? So clearly those services that are more critical, it's certainly much more my interest and responsibility to make sure that they can be sustained, because these are the things that only EGI.EU and its technical partners can deliver for the community in Europe as a whole. And then we start seeing as to who are consuming those services. The resource providers, the resource infrastructure providers in Europe, the NGIs, are clearly the main stakeholders at the moment within EGI and its activities. So in many ways, they are the ones that are calling the tune as to what EGI does. We need to understand how the role of those and the research communities fit into that. But clearly from my perspective, with the remit that's given me at the moment, the primary service consumer is the resource infrastructure provider, and what they are interested in is the service that they deliver to their research communities being maintained, and that means that the critical services and those that prevent the degradation of the infrastructure are the ones that we need to focus our energy and our funds around. So what do we need to do? We need to retain what we've already built. Throwing the baby out with the bathwater is not something we need to do at this juncture. That would destroy all of the credibility that the e-infrastructure community has built up over the last decade. They're critical for those that depend on them in terms of the service coordination and those that use them in terms of the resources that are being provided. But what we do need to do, and what we have been doing over the last 4 months or so, is identifying what are the critical services, how much they cost to deliver, and where do we expect to get the budget to support those. And plans have been presented to the EGI Council in Manchester a couple of weeks ago, and those are now being iterated around so that we can assure our research communities as to the level of service that they're going to get, the services that will be part of that portfolio, and how we see those being sustained as long as my stakeholders, the NGIs, and the IROs that are engaged want to carry on having those services delivered to them. So what are we doing next? I focused on the 3 strategic areas at the beginning, the community and coordination. We're investing in our human networks and the capital and the human capital that exists within them, and seeing how we can train those up. We have the EGI champions that have been established over the last 6 months, the NILs over the last year, the NGI operations managers that have been existing for years, and a new element in this, which is still a term, the EGI Geek Squad, recognizing the technology experts that we have across the product teams that were previously part of EMI and IGE, and trying to identify which are the experts in there that we need to engage with as part of our distributed set of experts so that they can engage with resource providers and with research communities to co-develop activities. The operational infrastructure, we will continue to operate, but we're also looking to see what can we do next. The EGI federated cloud activity that's been running over the last year now has around a dozen sites engaged in it. There's a standards-based interface to access that resource, and what we're now exploring is what is the initiative that could be introduced with European Commission to support to drive that federated cloud from its prototyping phase at the moment to where it might be in 2020 with 1 million cores and an exabyte of storage available to support the European research area through an open peer review and supporting the excellent science that we expect to see. And the virtual research environments that would then operate on top of that cloud environment for things to operate. So running through my final set of slides, we see EGI's activities moving into a set of platforms, a core infrastructure platform that is enabling other people to bring together their research centers and their research activities. And we see components of this already being used within EUDAT, and also components within this that are available for other research infrastructures that are being established. The cloud infrastructure platform is just one of the community platforms that can engage in the accounting and monitoring activities that are part of that core infrastructure. And on that provides a flexible way to deploy the software that researchers want to use where they want to use it on top of the cloud, or for those communities that have access to the resource centers directly to deploy those actually physically on hardware itself. And these put up a set of services for the European research area to use. So this all leads to a digital research infrastructure that's for researchers all over the place, using platforms as a way of building on top of that, and integrating this across a set of services across different flavors of resources. So this leads to the 3 lessons learned that I'd like to leave you with. 1, that one size does not fit all researchers. We tried that for the last 15 years. It's worked very well for the one research community. Other research communities are not particularly happy with that model. So as we move into the next phase, let's focus on openness and flexibility and personalization for the individual research community. That openness and innovation are essential. Technologies will continue to change. The federated cloud activities give one way of the research communities being able to have access to an open and flexible infrastructure. But we also then, behind that, need to be flexible in the technology we use. And sustainability is something that can't be put as a last month for the project deliverable. This is something that has to be brought forward as part of the core thinking. You can only sustain a certain set of services. Within a project, you can explore loads of things, but at the end of that project, you're going to have to make a choice as to which are the services that mean most to the communities and bring that forward as part of your sustainable core, and get used to swapping in and swapping out services as part of that sustainable core over time. That gives you credibility in what you deliver, and it gives you the ability to build a user community around that sustainable core that's going to stay with you through those changes. And so with that, I'll leave you with my concluding slide and invite you to the technical forum in Madrid in September. Thank you very much.
Questions for Stephen? No questions for Stephen?
Other than where's the lunch?
Yeah. Well, I do have a question. Where do you think EGI will be in 2020?
Aha, an excellent question. We'll still be here. I think there'll be a very clear set of services that the stakeholders, the participants, will be delivering. And EGI.eu and its partners throughout the whole of the community will be engaged in a set of support projects, innovation projects, and partnering with other projects in bringing in new technologies to refresh that service portfolio. And it's that sustainable service portfolio that now needs to be our focus, part of our focus in making sure we know what that is, and then building a set of projects that will change that service portfolio over time and make sure that the research communities have access to the services that they need when they need them.
Yeah. Another question I have is when it comes to Nordic collaboration. So EGI.eu talks directly to the national initiatives, the NGIs. What would you think could be an added value of a Nordic regional collaboration that EGI.eu talks to the Nordic initiative and not to the national initiative?
It's interesting that my first exposure within EG3 was to look at breaking down these regional structures into national structures. And I think we're now finding that the national structure sometimes doesn't have sufficient critical mass, and now the sort of the regional structure may have. From my perspective and from the team in EGI.eu, an effective regional structure is as good as a national structure. And we already have some national structures that are already federated together. So for instance, the Netherlands sort of takes care of Belgium in terms of the delivery of the operational infrastructure, even though they both have separate representation on the EGI Council. I think for the Nordics, the question would be, who speaks for the Nordics? Okay, in such a regional collaboration.
Right, yes, of course. So this, yes, Goodman, yes.
Yes.
Oh.
Yes, my question is, when it comes to the uptake of all these services that are being developed by EGI, how can we broaden the uptake of these services in the Nordic region? Would that be to expand on the Champions program that you have, or something else?
Yeah, I think the Champions program is one way of trying to build grassroots knowledge as to what the services EGI provides. The other model that we're looking for, perhaps in the next phase, is regional centres of excellence. The challenge that we have is still with not only we, but the HPC community, is on being able to access the resources and get your software running on it. The cloud, with the fact that that's becoming a more adopted model, may help us reduce that barriers by leveraging other tools and expertise. But there's still the need of an expert that will talk to a scientist and say, I now understand your data problem. This is how I can suggest that you go about analyzing it. And at the moment, we've not been able to scale that up from a technology perspective. We need to now focus perhaps on scaling up from a human perspective.
No further questions, so let's thank Stephen again.
Thank you.